Hi, I'm DJ Ware. On this episode of the CyberGizmo, we're going to be talking about the Berkeley Packet Filter, or as it's currently known, BPF. Right after this. BPF has been around a while, and I wanted to take a look at it because it has been enhanced a whole bunch over the past about 6 years or so. But what exactly is BPF, and why would I care about it? Why would you care about it? So BPF was called the Berkeley Packet Filter. It no longer is today. It is now just abbreviated BPF. But And today that includes something called enhanced BPF as well. So there are some things in it now that weren't in it originally. But BPF was invented about, 1992 or so, and was designed to speed up firewall operations by placing a virtual machine inside of the Unix kernel at that time. And that allowed BPF bytecode instructions, so that's kind of similar to the way Java does things. I hate using that comparison. It's not really fair, but everybody uses it. But it allows it to be, at that time, was interpreted into machine language and then run inside of the kernel. And today, BPF is a lot more than that. It does firewall operations. There are extensions to do performance engineering, a whole bunch of extensions. It allows for software-defined networks. In fact, without BPF, software-defined networks probably would have been very slow. I'm not saying they couldn't have been developed. I'm just saying they would have been extremely slow. Plus, it's also being used by a company named, I don't know if there's others, I think there are, but I know Cilium is probably more well-known. They are actually providing security through BPF to offer for containers because the Linux kernel itself, it doesn't know what a container is. So, yeah, that's what they're doing. It can also be used to write device drivers. So it's basically, I guess, basically a way to extend the kernel without having to get the kernel developers involved and without having to write a module. So, yeah, that's kind of what it's all about. So before we get into talking about this, let's point the blame back to where it occurred, where it all started. So, yeah, so why are we in this fix that we need something called user mode and kernel mode? Well, the original von Neumann architecture, which was developed in 1945, and believe it or not, that is still our view of it from software. I mean, it basically had your applications in the green area, and those ran to interface to the central processing unit. There was a control unit which managed just simple functions like being able to attach your program to a hardware address so you could read, and another hardware address so you could write. There was also an arithmetic unit which performed mathematics, and in those days it was pretty simple. What it provided, if you wanted anything else, your application had to write that itself. And then it allowed a single pipeline into memory, which generally was the bottleneck. Now, Intel and AMD certainly do not have hardware architectures on their chips that match that, but our view of it as application developers is exactly that model. So in other words, if I crashed a program here, I crashed the entire system. There was nothing to protect that system from crashing. If that system happened to have the ability to do multitasking, it would take all the workload with it. So one application goes down, everything goes down. So that led to, I mean, I'm leaving Multics out here, but Multics was really the one in between that really initiated this new design, which was to allow for multiple users and multiple applications running on the same box at the same time, while protecting the system or other applications that were running on it from a crash that one application might have. I mean, if you want a good example of that, just go back to some of the old Windows versions like 2.11, 3.0, 3.1, anything before NT. If you crash an application, chances are your whole system would go with it. Maybe not, but same with Mac, all the original Mac OS not Mac OS X, but Mac OS, which is way back. Even that, if an app crashed, chances are it would take the machine with it. But the idea behind this was to have hardware kind of surrounded by a layer, an onion, if you will, of other layers. And the first layer around the hardware was the kernel. And so the kernel was the only thing that could interface directly with the hardware. Everything else had to interface to the hardware through the kernel via an application programming interface, or syscall. And the kernel system did more than just manage the hardware. It also managed the system space in general. It allowed for memory management. It allowed access to the computer. So it controlled the security components of the system. It also maintained the file system. It also handled errors. It also performed all the I/O, and it managed the allocation of resources to the applications that wanted them. The shell, now this I'm saying is circa 72. Probably this drawing was probably created in 71, but I remember seeing it in 72, so that's the number I'm putting on it. So the shell was sort of a mediator between the kernel and the application program. So the application programs did not have a direct interface into the kernel. They had to make calls of the shell, and the shell would in turn pass those on to the kernel. So the shell had its feet both in the kernel space and in the user space. And then the shell allowed us to execute applications from a command line. It allowed us to change priorities of those applications that were running, and it would just pass that message on to the kernel on the kernel space. So it also acted like a command line interpreter, where it would allow you to do things like chain programs together. But the applications ran solely in user space, and of course we talked about that. If the application crashed, the kernel wasn't affected. Just the application and the application's data was affected. So if I had 10 programs running and one of them crashed, it didn't knock the other 9 of them down. So that was the whole idea behind that. But that user space to kernel space, I'm going to make a very simplified depiction of this. There's a lot more to it than what I'm talking about. But for today, this is probably all you need to know. When an application needs to get to the kernel, it has to send something called a system call. It has to make a request for that. Now, generally in higher level languages, let's say you just do an open file. The compiler underneath and the libc libraries underneath have translated that into syscalls. And those are that's the thing that's actually getting sent to the kernel. So it could be as simple as opening a file. It could be as simple as requesting a block of memory to be used by your application. But that forces a transfer of control. The kernel is running in its own space. I can't talk directly to it. There's a barrier there for me to do that. Also, the user space is running in its own, you can effectively think of it as a jail, I guess. So I have to somehow be able to not only take that information in the system call and send it to the kernel, but I also have to tell the kernel to transfer control to whatever that component is, so that it will execute in the system space, collect the kernel space, get some data, and then send it back to me. That is implemented as either a software interrupt or a trap. And the interrupt occurs, or interrupt, if you prefer, will transfer control to the operating system kernel. It allows the kernel to pick up whatever it was I put in the system call, or registers are included, or in whatever the interface call has. Allows the kernel to execute that system call and then return whatever results or data or whatever it is, or maybe it's nothing more than a return code to say, yeah, I completed it, or no, it failed. In RISC computers, that's the only way to do it. But there are some other ways that the x86 architecture, particularly with Intel and AMD, offer in order to be able to do those syscalls more efficiently. And they have implemented a syscall and a syscall return, and then the other one has implemented a sysenter or a sysexit call. And those are built into the CPU instruction set, so they do not take a whole lot of time to run. So that has simplified things a bit. There used to be a call gate in the older x86s, and it took a while before it would actually transfer code. if, God forbid, you're running any IA64 based CPUs, you use EPC, which is the interprivileged code execution instruction. So, yeah, you have to actually request permission to run as privileged code, and then you can send your call across first in that environment. So I think you probably can see that this is going to take quite a bit of time to do, because I've got to take data, I've got to set it up, I've got to make a call, I've got to interrupt the kernel from whatever it was doing, and then tell it to go do the system call, and then come back to me, and then release the kernel to go do its thing, and then I have to take the data in and get a reinsstantiation into the schedule to execute and do my thing. So yeah, that is pretty slow. And what was going on in the early days with firewall development, particularly with those pieces of software that ran in Userspace, is as the speeds of the network went up, they got slower and slower at interpreting the packets, and it got to the point where they were consuming the processor. And so that's probably not a good thing. If you're running a firewall on the same box as you might have other application code, you don't really want the firewall to take all that much of the CPU, do you? But as it increased, it was clear that something had to be done. As we went from 1 megabits per second to 10 to 100, it just got serious. So the other problem that occurs is if you're in Userspace and you accept a packet, you're the one that gets to process it, because if you don't, it gets dropped. If you don't send it back out the other side, then yeah, it gets dropped and it's gone. So yeah, kind of a problem. If you want more information about that, I'll put some links about some of the development that you can do with networking. But I think that's a topic for another time, really. So clearly we needed something faster here, because we couldn't let this go on forever. So Stephen McCain and Van Jacobson. Van had done a lot of work in the networking and the communication space prior to this, but both of them were working in 1992 at the Lawrence Berkeley Labs. And they created what they called the Berkeley Packet Filter. And this was the first, people refer to this sometimes as classic BPF or just BPF by itself. So it is kind of confusing. And I kind of agree that maybe we should just call it BPF. But the idea behind it was to create a virtual machine. Now I don't mean virtual machine in terms of a VMware virtual machine, more like a virtual machine, like a Java virtual machine, which sits inside the kernel and takes bytecodes and interprets it to machine language. And that would allow a series of functions to occur to verify and make sure that that code isn't going to crash. If it crashes in the kernel space, well, the only exit that the kernel has is panic. So yeah, it doesn't return errors if it has a problem. It just crashes. So you don't want that to happen through BPF. So we'll talk more about that when we get to it. Well, so for the first time, BPF allowed a user application to call a limited set of functions in the kernel without having to do a software interrupt to do it. So once that was set up, once the initial system was set up between the BPF that ran in Userspace, the application that I started, and the application that was running in the kernel space, they could freely exchange data. And so I didn't have to have this interrupt every time I wanted to move data back and forth between the kernel and the user space. So that sped up the firewall performance by 20%, about 20 times. That sped up the firewall performance. So yeah, that was pretty big, especially with those machines back then that were pretty slow. Enhanced BPF came along 2014, I think, and it included a just-in-time compiler. It also opened up some additional system calls that could be, or those execution control points. We'll talk more about that later. But that allowed a lot more things that could be done with BPF than just managing packets. So, but the main thing was the just-in-time compiler. So now I didn't have to keep reinterpreting that bytecode over and over again every time I came through a loop. So I now had a place where I could run machine language directly, and that sped up things another 4 times. So yeah, and that was pretty significant. So BPF was kind of extended along the way in part. So the initial eBPF was initially added to the Linux 3.18 kernel in 2014. The 4.x added additional capabilities and opened it up a little wider, gave it more control points. I think there are, I haven't counted these, but there are probably close to 1,000 different control points now that you can attach to. The Linux 5 kernel corrects some of the problems that were exposed by Spectre Meltdown, some of the vulnerabilities. It also expanded the size of an eBPF application. I'm sure that it also added additional system calls. I just don't know what those are offhand. So I guess if you really want to play with a feature-complete version of BPF, you can accomplish it with anything higher than 4.9 on the kernel. If you want larger applications, because you're kind of constrained on 4.9 to 4K eBPF programs that are running in the on the kernel side. So yeah, you're kind of restricted there a little bit, but there's quite a bit you can do. But 5.3 opens it up to about 1 million. Yeah, so it's quite a bit larger. And I bet you if you went and complained and it wasn't big enough, I'm sure that they would expand that for you. So it's kind of led to a running joke that BPF will replace Linux. I doubt it, but maybe, you never know. BPF is event-based, not interrupt-based. So event-based operating systems do have their advantages. They also have their disadvantages. Remember, I've said this before. Any new solution comes with its own unique set of problems, and maybe that's a jaded view of technology. I don't think so, because there's always things we forget about, and we concentrate on solving one problem and we forget about something else and create a new problem. So there are some security concerns with BPF. BPF is essentially, for all practical purposes, a means to code inject into the kernel directly. So yeah, if you're not careful, and they have thought of that. The BPF does have boundaries around things. There is a virtual machine. There is a verifier that looks for that kind of stuff. And but Spectre Meltdown showed that we could get around it. Because I remember the early researchers were looking at BPF, and they were able to, through the BPF interpreter, be able to gain access to memory locations in the kernel that were not protected by the BPF verifier. So anyway, yeah, there are definitely some concerns there with that. So just be aware of that. So how does this thing work? So in the 3.18 kernel, they introduced a new system call called BPF. And it might have been in 1992, but I'm pretty sure, yeah, well, it might have been in 92. But anyway, the Userspace application is what you write. And that application contains the BPF binary in it, and the compiler does that for you. You don't have to do that. And typically, you use GCC, or you use CLang or Clang if you prefer. And also LLVM also will generate this as well. So there are some helper apps, like there's some Python scripts you can run and some Go scripts you can run that will help kind of build all this stuff up that you need in order to create that BPF call that then allows the BPF to be loaded into the verifier. At that point, once you made the call, your code is moved into the verifier, and it begins looking at it. Currently, BPF does not support unbounded loops. So if you have an unbounded loop, it's going to shoot you back out, and it's going to say, no, you can't run. So I don't know if they're going to ever fix that. It's not really a problem. It's a problem for the kernel, but it's not really a problem. But I don't know. But anyway, it's there. They also check some other things, like if you're trying to sneak outside of the boundaries of your allocated memory. Once the verifier is happy, it moves your bytecode over to either the interpreter or the just-in-time compiler. And that then determines, you would in your application, your BPF code would say, this is the control point I want to attach to. Say it's a syscall of some kind. And then the interpreter or the JIT would say, oh, I got to attach a BPF helper because I need to be able to help you get access to the control point you asked for, so that it has all the necessary APIs that you need for that particular type of control point. So it would do that. At that point, you can then create something called a BPF map. And a BPF map is essentially a space of memory that's allocated for you to store in. You can put data structures in there. You can put in key value pairs. But the cool thing about it is that is how data is transferred bidirectionally between the user side of your BPF program and the system side of the BPF program. And that can occur bidirectionally. So you can read and write it from the user space. You can read and write it from the kernel space. It's kind of neat. And then you would have your other subsystems that you were looking at or monitoring or doing something with. So, and that's a really simplified view. I'll recommend some books later that go into more depth of how this works for you. So, yeah, don't take this as this is exactly how it works, because it's not. It's just a simplified view. So, of course, we talked about the new system call that was added to the Linux kernel called BPF, and that serves as the control point of communication between the user and the kernel space. It also added the BPF maps, and we talked about that. That's the bidirectional mechanism to exchange data. It does use high-level languages. You can use wrappers inside of Python and Go and Ruby, and there's a bunch of others. But the BPF verifier makes sure that nothing in your code would cause the kernel to exit to panic. We don't want that. And then the BPF bytecode is then executed using the interpreter or the JIT. There's no need to restart your system to run it. I mean, if you remember, if you load a module, you got to do something. You got to stop the program, load the module, start the program. So you can do this all on demand. There's nothing, once you've got the stuff installed, there's nothing you got to do other than tell it what control point you want to attach to. And you can write your own scripts to load the BPF if you wish, and so that those BPF applications come up like a system service. If you want to. So before the kernel runs the BPF, it needs to know, let's talk about that execution control point a bit. So these are attachment points within the kernel, and that list is growing. There are literally thousands of control points that you can attach to. So once your program is chosen, that is, you have chosen an execution point, I'm not going to get into all of those today. I think that might be a part 2 to this, where we talk about that a little bit more. But just keep in mind that you have to attach to something that you want to look at, right? I mean, if I want to monitor performance on the I/O subsystem, I have to attach myself to something that is monitoring, in the kernel on the I/O points. So that would be the execution control point. Then BPF, we talked about the helper function, and so that makes your BPF program and the execution points tightly coupled. So, yeah, you can't dynamically change that in the BPF and say, oh, I see a problem in the syscalls for the number of latency on how long it's taking to load a program. I want to go check memory. You can't do that. Sorry. Once you attach to a control point, you're done. You're locked in. So yeah, you would have to have another BPF program. Now, you can chain BPF applications together. Yes, that's not for today. But so then you can move data back and forth between the user side, so you can report it to the person that's sitting at the terminal staring at it, wondering what's going on in the system. And then once that user exits the BPF program on the user side, it automatically terminates the kernel side. So there's nothing you have to do there. I think probably the best way to kind of show this is to switch over to this, maybe. Let's see, full screen, that's what I want. Okay, so I'm going to go, I've got a system set up called Green Ice. I'm running under Ubuntu. Believe it or not, Ubuntu has better support than any of the other operating systems so far. And you will let me do an apt search here. And I'll do a more, so you can see all the things that are available. but there's only a few of these that we're really interested in. So the first thing you'll want is this, the BPF CC tools. And that has the compiler and a collection of utilities that you can use out of the box. So you don't have to be a programmer to use this. There's some tools that the community has very kindly donated to allow you to monitor things in your system, which is really nice. And then the other thing you will probably need is the BCC, which is inside that, by the way. So you'll also need some kernel. You'll need some kernel libraries. I will put in the link below a link to one of the pages that that I use to set this up, so you can follow the steps directly in setting it up. But one of the things that you will find in here right away is, hopefully you can see that. So if you look at the sbin directory, you'll see all of these files with BPFCC. These are BPF applications that have been written for us. So I'm going to start up another terminal because I'm going to need that. If I'm going to do any monitoring, I can only monitor with one. Can't. All right, so I'll leave that there for now. Let's do a man on OpenSnoop. And OpenSnoop is one of the tools provided with the GCC toolkit, and that allows you to trace system calls. So every time there's a software interrupt that's called to make a call on the kernel to do something, this will look at it and display what was done. This is really helpful if you're trying to find where's the log file for this application, where did it go? Or if you're trying to find out what caused the application to crash, for example. Or maybe you're just interested in what the overall load is of your system. So let's do this. You have to be root, of course. You have to sudo. Now that's not going to run for me until I do this, because I need to tack that on. So I can just put that in all by itself. And now, right now, it's pushing it through the verifier. It's setting this up. And right now, it's just waiting on anything that's calling the system. And you can see there's already some calls that are going by. These are this is the normal SMP affinity stuff that goes on in the kernel to determine the balance and the load of the system. And then there's a check on the thermals on the CPU to see whether or not to turn the fan on or off. So I'm gonna go ahead and SSH, and you just saw a whole bunch of calls there as SSH went in. So I think you can kind of get an idea of what this is actually doing. It's also telling me the priority that this is running at. So if I run htop, you'll see a bunch more. As htop starts to collect every so often, you'll see it pull in the kernel over and over again for stuff. So yeah, OpenSnoop is kind of nice, and you can kind of leave that run for a while if you just want to kind of see how things are flowing in your system. Let's give it something to actually do. I think I have some benchmark programs out here. So yeah, very conveniently I do. So let's do, I'm going to need a sudo, a shell /nash bench. Let's do file sequence, that shell. Now this isn't going to generate a whole bunch of stuff, but you just saw it just flew by with a whole bunch of stuff already. Oh, it's asking me for the account verification. Okay, so now at this point, file is generating IOs. And so you can kind of see file flying by here on the side as it completes its work. That's nice, but so what, right? So what? There's also, I need to be under sudo exec snoop -bpfcc. And all this one does is it monitors applications that are coming into memory. So if I type in htop, it tells me the name of and the location of the program. If I put in top, it tells me that. And if I put in my file command again. It tells me here's the command line that the application sent. Basically, that's it. That's all it tells me. Let's find something a little bit more interesting, though. Let's see. I've got some that I did earlier. In fact, I got a lot I did earlier. H tells me the help. I think there was one. Yeah, that one. So in this case, it's going to go over and set itself up. Now, if I run my file benchmark, this is going to monitor the I/O ports. This is block I/O, not BIO. It's block I/O. So this is looking for any block I/O that's going on in the system. It doesn't do anything until you do a Control-C, because right now it's gathering the statistics and storing them in the BPF map. So if I do a Control-C, it shows me a nice little histogram of how long in microseconds that particular I/O took. Let's give it something a little bit more useful, though. Let's see. NAS, bench, DH5. We'll run IO zone. Let me get this back up so it's ready. There we go. And you can look through. I'll show you the list of stuff that's actually provided here. This is really good. I mean, you can look at stuff like this to see whether or not you're. If I had an SLA that said I had to maintain at least 2048 nanoseconds of latency, and I had to stay under it, then I can look at a histogram like that. I'll notice some outliers, but the vast majority of the IOs were definitely underneath that. So yeah, if you're in an SLA situation and you want to know how you're doing, this kind of thing is pretty nice. So I don't know if I'm going to let this run all the way through. I don't think so, because there's another way to run it that I want to show you. So I'll do a Control-C. And so for that entire run, the preponderance of the IOs took place here. There's some outliers on either side. That's kind of expected. You know, if I run this for a few days, you should see a bell curve. That's kind of normal in distribution plots. So yeah, this is kind of not normal because there's not enough data to fill it in. But the other thing you can look at, if I put in a -Q, I can look at how long did it sit waiting for the kernel to get to it. So yeah, if you're doing Q theory, this is kind of important, because in performance engineering, that's kind of what it's all about, is planning and predicting the impact of a load on a system. Do I need to add channels? Do I need to add more drives? Do I need an additional system or an additional controller? What do I need to be able to solve this problem of Q depth? Now, Q depth isn't always bad, unless it becomes excessive, and then it becomes the bottleneck. And then, so that's part of performance engineering. I'm not going to get into all of that today. I just kind of wanted to give you a flavor for how this works. This is actually running BPF code. This has actually got code in the user space, and it has code in the kernel space, and is actually doing stuff. So you can play around with this, and I'll show you the list. I'm going to let this all finish, though. I want to run this all the way through. Just see if I can collect enough data. What this is doing is it's adding on users on each iteration of each benchmark step. So if you looked at the benchmark videos, you probably already know what this is doing. But it starts with one user, then it goes through the complete list of tests, then it adds the second user, goes through the complete list of tests, and then so on, up to 5. So I don't know if I'm going to let this thing run all the way out. I might let it go to 3. And then it's up to the last part before it does 3 anyway. So we're done, and there's my report. I did a Control-C. So if you want to see all of them, let's go over to SBIN. And there are tons. There are man pages for all of these. You do not have to put in, you can, but you don't have to put in the dash BPFCC. I think the reason why they did this was to prevent it from colliding with any application packages that you might be using that use the old Userspace method of checking data. So I think they did that. So if you know that you aren't going to collide, I guess you could change these to the shortened name. But yeah, you can see that you've got hard IQ, file top. They have all kinds of stuff in here. And like I said, I'll recommend a couple of books at the end of this for you that you might, if you're interested in this and want to pursue it further. But that's pretty much what I wanted to show for today. So let's talk about some of the conclusions here a little bit. So what is BPF? Well, it offers us the ability to extend the kernel without having to involve the developers of the kernel. I don't have to have a module written. I don't have to have a control point written in order for that module to attach to. It offers me the ability to monitor kernel calls without generating the overhead that a user to kernel space software interrupt would create. So yeah, it would be even worse in these modern systems where you're really flying with a lot of interrupts. I think if you saw the benchmarks on the where it was recording back on the number of tools and some of the tools you could see, yeah, you would be handling an awful lot of data. It also provides a safe virtual machine to, and not remember, this is not a virtual machine like VMware. This is a virtual machine like Java to run a kernel space code without endangering the stability of your system. And a couple of buts. I said one, but there's really a couple. Yeah, there's some security concerns about it because it is a method to code inject into the kernel. The other thing is that BPF is not Turing complete. Now, for most of you, you probably don't care, but Turing complete means that there isn't enough function in the language to allow it to simulate one of Alan Turing's machines. That's important for language developers to be able to be compliant with Turing completeness. That's why all of our languages have integers and real numbers, and they have loops, and they have control breaks and all those things in it. Those were mandated by the Turing machine, and it is the basis by which computability is determined for an application or a programming language. So yeah, so it doesn't, is that a big deal? Nah, it's not a big deal for what this is being used for, but if it becomes to the point where they're starting to develop device drivers, yeah, it's a big deal because we want portability. We want to be able to move stuff and expect it to run in a similar way from one machine to another. So with that, I think my intent today wasn't to educate you completely on BPF. We don't have enough time for that. But I will recommend some books. I will come back at a later date and do a part 2, show you how to actually develop some code in BPF, and maybe we'll go from there and see what y'all think. Some of these ideas, they kind of fly. Some of these ideas don't. So I'm just kind of exploring what you might be interested in. If you are interested in learning more about this, let me know in the comments below. And as always, please like and subscribe, and hope to see you again real soon, and bye for now.